And you do see the title page, right? Files and directories. Is that true?
I see it. Yeah.
Okay,
Yes.
good, good, good. I always, because I got another screen here, I always get encouraged when I see the green border around it. When I don't see the green border, I know something is wrong. Okay. All right, files and directories. So now we look at the different types of files: ordinary file, directory, special files, primarily. We'll look at the actual file system structure as it applies to X. We'll look at what is a root, what is /usr, what is /var and such. And we'll look at using both full or absolute path and also relative path names in file specification. We'll look at how to create, delete, and list contents of directories, create a directory, delete a directory, but also using the ls command to list the contents of a directory. And we'll use the touch command to create a file that's 0 bytes in length, or in other words, an empty file. Okay. So now we want to kind of work with some working definitions here. I mentioned the definition of a file system. So now we'll kind of write this out now because we're moving along in the class. So a file, simple file, is a collection of data. Now, if we look back at this morning, I kind of put up, if you will, AX storage hierarchy, and I'll go back to that once again. And we had, once again, our AX fundamental basic storage hierarchy. Okay, all right. And that included, once again, a volume group. So we'll put that here, a VG. So a VG, or a volume group, come on, get in there, which is, as we'll see, a collection of one or more physical volumes. So that's a volume group. I wish I could write it in between. I want to try this, okay? Okay. So a volume group is a collection of one or more physical volumes. And again, that next layer will be physical volumes, or disk, if you will. Okay, one or more in a volume group. And then the next layer we have is the actual logical volume layer, where the logical volume manager operates at. So this is by our logical volumes. And AX uses the concept, more precise, the logical volume manager uses the concept of logical volumes to address our logical to physical storage mapping. Okay, so whether it's a paging space LV, a log logical volume, or a logical volume that contains a file system, or whatever, the storage is always mapped logically to physically through the use of a logical volume by the logical volume manager device driver. And then, of course, we have the file system, which I'll put here, because once again, a logical volume can contain the structure of a raw device, or a file system, or a paging space. But again, in this case, we're speaking of a relationship between a logical volume and a file system, okay? And the next layer, of course, would be directory. So I'm just gonna go down here because I do have enough space for a file, but I'll put it here. Directory. And then, of course, the next layer down would be the actual individual file. Shorten that up a little bit. And the individual file. So this is kind of like our fundamental storage hierarchy. Once again, we'll be working in the region, in the area, if you will, of directories and files, okay, within the /home file system. Okay. So now let's go back to our working definition of what is a file. Okay. So let me put my arrow here. So what is a file? A file is a collection of data, a stream of characters, or a byte stream. Okay. Characters, collection of data. Collection of data, saying that no structure is really imposed on an individual file by the OS. The application, the user, is responsible really for the actual structure, if you will, if there's any to be, within the actual file content. All right. Now that's different than the definition of a file system. So we'll look at a versus a file system here. So we'll say a file system, if you will, come here, is really when it comes down to it, pretty much we'll say a hierarchical method. We kind of use this definition this morning, hierarchical method, if you will, of actual storing data, okay? Storing data. Now, within that, if you will, okay, storing data, that file system, if you will, is composed of files and directories, okay? Our example would be operating within the /home file system, okay? So a file system being a hierarchical method of storing data composed of files, composed of directories, and again, like we mentioned this morning, within that particular file system, okay, then the file system, okay, we mentioned this morning what store, retrieve, and also update data, right? Or update files, we'll keep it more specific, okay? And the file system also organizes the data within it, or organizes more precisely the files and directories, the data associated with the files and directories by using the structure of inodes and such to point to the data blocks within the files, within the structure of that particular file system, whether it be JFS, JFS2, NFS, CD-ROM, or whatever type of physical file system, okay? So the definition of a file versus file system. In this class, we don't deal so much with the file system. Okay, everything is basic, everything is file. But just to draw a comparison, just to draw a parallel, we have our file, and then we have, of course, our file system. Okay, we'll be working for the 15th time within the actual /home file system primarily. Our examples will be that, and also within our lab structure will be associated with the /home file system. Okay. Any questions about anything on this page? I know we added some things. Hopefully they are helpful to get everybody going. So I guess now we'll take a look at the different file types. So let's clear all the drawings. Okay. Save that and go to the next page. Everything should be fine. See, it left this just like I said. Okay. All right. So the three primary file types. Again, these are the three primary file types. But let's make a statement, and you probably know this already. Okay, that for the most part, everything in Unix world, AX. So we can say, without a doubt, in uppercase letters, everything. Okay, okay. In Unix and AX, or we'll mention AX first, is represented by some type of file. Is represented by some type of file. All right. Whether it's an ordinary file, whether it's a special file, whether it's a link file, whether it's a socket, whatever is in Unix, everything in Unix, whatever device is represented by some type of file. All right. So we look at the construct here of our different file types. We have, for example, ordinary files, directories, and also special files. Okay. Now, ordinary file is just simple text or coded data. Files exist within the structure of a directory. And they simply say here, a directory is a table of contents that stores a list of files within that particular directory. Now, again, for those of you who are old enough, you might remember file cabinets and such. We can kind of say, for example, a directory has an analogy or is analogous, if you will. If I can analogous. Okay. What is wrong with this jumping around? analogous with, if you will, a file cabinet. Say with a file cabinet. Whereby, if you will, the file cabinet actually is used to what? Store files, store folders, and that folder stores files within those particular folders. So like it says here, a table of contents directory, that is, that stores a list of files. For the most part, the only thing that's listed in a directory is the actual inode number and the file name. So that's what it's saying here. It's more, operates more like, if you will, a filing cabinet or a file cabinet, because the directory really does this. We'll say it, come here, text. That should have been one L, two L's with analogy, okay? So in other words, just the name and inode number are stored within the directory, okay? And the directory actually groups, if you will, files into separate folders, if you want to call them that, folders being highlighted, accented, okay, quoted, if you will, because it doesn't actually use folders, but separate folders, if you will, and those folders are associated with an inode number, inode and inode number. Extend this out this way. All right. That's kind of what the directory is, okay? So the directory contains a list of files, okay? And normally within a directory, only the file name and also the actual, if you will, inode number. And then of course we can use commands like ls-l, which will list the inode information for those files within that particular directory, okay? And from a standpoint of architecture, structure, if you will, by only containing or only hosting or holding, if you will, the inode number and the name of the file, this makes more efficient, if you will, disk-based usage, as opposed to having the inode numbers that point to the actual data blocks, and then the directory stores the inode numbers and such in the data blocks for that particular file. So in other words, it minimizes this duplication of the content of the files associated with those directories. Okay? So file types, ordinary file, directory. And then there's of the many different file types, the three primary file types. And again, now we have special files, okay? Now special files, again, are special for a reason. And for the most part, special files represent some type of device driver, but we can kind of say they represent hardware or logical devices. We can simply say also represent virtual devices also, because virtual devices will have an associated special file within the /devices directory. The special files are what the kernel uses, if you will. The kernel uses this for access and control of devices. Just make this out. Okay. And really, what's the access and control of devices? And really what this represents, once again, is, okay, we can say it specifies whether a device driver is loaded. And I'll put loaded in quotes. Because if the device driver is loaded, then there would be an entry in the /devices directory. And the reason I say that is because I can point to this, because an example of a special file that says here, the CD-ROM device is accessed through the special file entry /dev/CD0. If it's hdisk0, it would be /devices/hdisk0, because there would be an entry for that particular device in or within the /devices directory. All right. So we have ordinary files, ordinary text files. We have directories, which again, basically a table of contents that stores a list of files contained within that particular directory and such. And then of course, there are special files, which the kernel uses for access and control of devices. But really, those are device driver files. Device driver is just software code that allows the operating system, in that case being a kernel, to actually operate or function against or with that particular device. All right. So to keep this simple, we'll just talk about file types being ordinary and directory. That pretty much will be what this unit is about, not so much special files. But keep in mind, everything in Unix X is represented by some type of file. Any questions about anything thus far? Okay. All right. So now let's talk about inodes a little bit. Let's see if it works this time. Clear all drawings. Yeah. Nothing left, right? Okay. All right. Directory contents. Remember, a directory, a table of contents that stores a list of files within that particular directory. So we have the directory, and then we have what we call the inode table, if you will. Okay. Now, this is figure, because I don't have page numbers, this is figure 4-4. Okay. Directory inode. So the customer is opening the file, my file, using the VI command. Okay. In this case, that opens the contents of a file. Now let's say something about inodes, okay? Because they have what the directory represents. Remember the name of the file and the inode number. But by using different commands, like for example, ls-l, we can list out the content of a directory, including the file type, permission bits, and such. But let's define what an inode is first, okay? So annotate. So the inode. The inode, simply known as an index pointer, if you will, but we'll keep it simple, contains all known information. Just want to stretch it out. Contains all known information about the file. All right. So all known information about the file is stored in the inode, and that represented or is represented, if you will, by by the type of file. Okay. Well, we'll start with the inode number, the type of file, the permission bits, what they call here the mode, okay, whether we have read, write, execute against a particular file directory, the number of links established to that particular file. By default, directories will have 2 links. By default, ordinary files, by default, will have 1 link. We'll talk about links and such in unit 5. The actual user and the primary group that this user created that particular file or directory, rather directory being a type of file, in this case, team01, primary group staff, default for ordinary user. And then the date is the actual last update to the contents of that particular file. And then the size as far as the number of bytes. And again, the inode points to the actual data, in this case, to the data blocks or the location of that particular file, in this case, on disk. So the directory contains the name and inode number 4, inode number 10. Inode number 4 is a directory by the name of subdir, okay? And then my file is inode number 10. Again, we see the different permission bits, and we'll talk about these octal numbers later, but really a 755 represents read, write, execute for the owner, 5, read and execute for the group, 5, read and execute for all others. We'll break down those permission bits as we move along this unit and also the next unit. Okay. So the inode, if you will, contains, how did this get partially erased? Contains all, it should be, well, I guess I should erase it because I'm not spelling. Contains all known information about, we'll say, the file. Okay. And also with the inode number, keep in mind that the actual inode, we can say, serves as pointers to the actual data blocks. I'll extend that out. Okay. So the inodes serve as pointers. We said that they were index pointers to the actual data blocks that contain the data associated with that particular file. Okay. Any questions about any of those things? Keep in mind the mode here represents the actual access permissions to that particular file. And just as a little exercise here, we'll just break down what the 755 is. In this case, come here. want to draw the 755, okay? And we'll talk about these permission bits later, but for example, a read is equivalent to an octal value of 4, a write is equivalent to an octal value of a 2, and an execute is equivalent to an octal value of a 1. So 4 plus 2 plus 1 would be 7, right? If you had read, write, and execute. So this is how this would look, okay? And again, we'll be looking at this later, so have no fear about this, okay? So we have the permission bits for the owner, then we have for the group, and then we have for others, okay? So the permission bits would come out, for example, would be read, write, execute. 4 plus 2 plus 1 is 7 for the owner of the file. Then the next field will represent the group. 5 would be what? Read and execute. 4 plus 1, so that would be read dash execute permission for the group. And the same thing would be for all others who are not a group member or the owner of the file. And that 5 there represent read and execute permission. Okay, no write permission, but read and execute permission. Read and execute permission, okay, for all others within or associated or can have access to that particular file. So that's what the 755, those are actually octal values that we'll break down. You can kind of see by utilizing that read equals 4, write equals 2, execute equals 1. You can kind of break it down for the actual ordinary files, okay? But again, the 7, why is it 755 by default? Why is it 644 by default? And we'll be talking about later on this term called a UMask, okay? So keep that in mind. The UMask that's set for the actual system determines what the default permissions will be when you create a directory and what the default permissions will be when you create a file. That's what we call a UMask. And again, we'll be studying all these things as we move along through this unit and also the next unit. See, left that, right? All right, AIX file systems, okay? Now let's kind of like do a new share real quick, kind of go back out to share the screen, okay, and resume share on that screen so you have everything so everyone should be able to see this, okay? Now, we mentioned this morning when we typed in the mount command, this shows us all of the currently mounted file systems, okay? All right. We can also use DF to display file systems. We can display the amount in megabyte. That gives us a few more fields, how much free space is remaining, this and that. And this is displayed in lowercase m in megabyte. You can use lowercase g for gigabyte or lowercase k for kilobyte also, all right? But usually an admin is looking at this df-m to see how much free space, that free column, how much free space is remaining within that particular file system and what percent of that space is currently used. If it approaches like 80, 90%, you start to get a little nervous. 95%, very nervous, because again, your free space is diminished within that particular file system, okay? Now, outside of that, let's get back to our regularly scheduled program. We just take a look at file systems, okay? There will be default file systems and default logic volumes for a root volume group. We can use an administrative command like lsvg-l against the root volume group. That's the only volume group we have configured. Now, some of these logic volumes like HD5, these are logical HD8, do not contain the structure of a file system, right? That's what you see here. But HD4 contains root, which again, we see slash down here later on. HD2 always associate with slash USR. HD9 var always associate with var. The logic volume HD3 always associate with slash TMP. And I mentioned slash home, HD1 logic volume is always associated with slash home, which is what you'll be working with primarily in that file system this week, okay? So these are the default root volume group logic volumes and also the default root volume group file systems. And what I mean by default is when we install the operating system, when we install AIX, this is pretty much what you get, okay? Now, for the purpose of the lab environment, they did create a separate dump logic volume, which again is not created by default unless the memory size is greater than 12 gigabyte, okay? large dump LB. Okay? So everything you see here for the most part is created when we install the operating system. Okay? So let's go back to our file system share. Okay? All right. And this is, everyone is seeing what? The actual AX file system screen, right? Yes, no, maybe so. Let me know.
Yes.
Yes, good, 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 good. That's all I wanted to hear. Okay, because I know this thing, everything is saying green border, should be good. Now, in AX, we gave a definition of a file system a couple of pages back. It is what? A hierarchical method of storing data. Okay. So in AX, a file system is an allocation of storage based upon the physical partition size and the physical partitions in that particular volume group. In other words, when we create a file system, we create it at a specified size. So in other words, that is where the allocation of storage from the volume group comes in at, because all storage fundamentally in AIX is allocated from the volume group. That goes back to our storage hierarchy, and that's why I kind of drew that out. Even though it's not part of this class, the better understanding you have, if you don't have that already, then we can kind of put things together a little bit quicker. So now we're looking at that layer, the file system, and that file system is created by allocating storage to it. Now, just to sidetrack a little bit, let's go back to, again, give you a new share. Okay. This is not part of this class, but just remember this just for purposes. I'll use SMIT, okay? Okay. And I want to work with storage, so I come down to system storage, physical and logical storage. Okay. Okay. All right. And in this case, I can work with logical volumes, I can work with physical volumes, I can work with paging space. Okay. All right. Or I go back a screen, I want to work with file systems. Okay. Okay. Let's say I want to add a file system. So I would choose the third selection there, add, change, show, delete. Okay. And then what type of file system do I want to create? I want to create a JFS2, which is referred to as an enhanced journal file system. So I would choose JFS, and then, do I want to add it? Have I already created a large volume? Nope, I just want to add it. I want to add it to the root volume group because all storage is allocated from the volume group. And that's what you see here. I only have one volume group configured, so therefore I have to choose root VG to allocate the storage from. And then you see here, okay, doesn't ask me for a name. It's just the volume group name and then the size. How much space do I want to allocate to this file system in megabyte? Or I can use the escape 4 key. I can allocate it in megabyte, gigabyte, or 512 bytes. But the default nowadays is still megabyte. But I could create it in gigabyte or up to that much megabyte to get to the gigabyte. Again, outside of the bounds of this particular class. Okay, so let's go back to our share. So now we look back at file systems. Okay, let me pause share just to make sure. Zoom share, we got that. So file systems refers to both, if you will, the physical and logical storage. Okay, but also when we create the file system, there's a directory structure which could contain one or more files. So this refers to, when we're simply speaking about file systems, to both the physical and logical storage. Keeping in mind the LVM allocates storage logical to physical mapping. There cannot be any logical volumes without some physical storage. There cannot be a volume group without physical storage. So again, it says here, file system in AX or Unix is similar in concepts to partitions in the PC environment. Okay. And we said earlier, allows the OS to store and retrieve data. That was part of our definition for a file system. And of course, we can actually use file systems for different purposes, different security methods, different mount points, and also different storage as far as allocation. When you install the operating system, X has several predefined default, if you will, file systems. And we just pointed those out. But once again, before we go on break a little bit, let's see, annotate. We'll highlight, spotlight. So root, and again, every file system, as we saw, is associated with a logic point, right? So root is associated with device HT4, /USR, /var, /temp, /home, primary for user, ordinary users files, admin, okay, proc, and also opt, okay? So these are what they call the X several predefined file systems, and these have been the predefined file systems since version 5.3. Root, USR, var, and temp and home have always been there. At 5.3, they added admin, proc, and op as part of the default root VG created file systems, okay? All right. Okay, now that our brains are filled up a little bit, let's do this. Okay, let me clear all the drawings, clear all mine. Yeah.
I have a question, Ed.
Yes, go ahead, please.
Would there be actually a /etc?
A /, that's a directory. Yeah, and we'll talk about our next.
There it is.
Yeah, that's a directory. Yeah, because some file systems are the same name as directories of which they operate under. Yep. Yep, good question. And we'll talk about that one after the break. All right. So our new share, we'll go up here because we always keep ourselves fresh in this class. We'll take a 10-minute break. Okay, we'll give everyone a few moments to get back. Okay, continuing figure 4-6, but before we start at our next break, which will be about somewhere about so I would say 4:45 Eastern time. Again, we'll go to labs for the remainder of the day, which again will include exercise 2 and also exercise 3. So that would take about 45 minutes to complete those. So we'll have roughly, of class time, an hour to accomplish those 2 labs. So at our next break, we'll be going to labs for the remainder of the day. So we look at our hierarchical structure here as far as the file system structure with X on figure 4-6. Keeping in mind that this is our inverted tree structure, if you will. Everything begins at the root. So in other words, this structure here represents only a portion of a typical AIX file system. But again, it contains the primary components, if you will, of this AX file system. So in other words, the tree structure always starts at root. Root is inverted. Root is at the top as opposed to the bottom. So what they have here listed as far as the actual slides, the visuals are the actual blocks or squares, if you will, that have blue or are framed in blue. These represent, in addition to directories, but also represent file system names or file systems, if you will. So for example, / represents the root file system, okay? USR is a directory, but it also is a file system /USR, okay? I'll just do the blues first and then we'll come back to the regular directories. /home represents the home directory, / being root home, but also the home file system. var represents the /var directory, root var directory, but also the var file system. Temp, same thing. Opt, optional, same thing. Also proc, same thing. Now, these remaining directories that are, if you will, bordered in black, like dev, represents the /devices directory. This is the directory /dev, whereby special file entries are contained, like we mentioned a few moments ago, where the actual, if the device has a device driver loaded, it will have an entry within the /devices directory. Okay. Excuse me. Then we have the etc or etc, not a file system, but a directory directly under root, if you will. The system binaries or sbin directory under root. There's also a binary directory under /usr, if you will. And of course, we have on the home, notice we have, again, the home file system will contain normally our user associated files, like in this case, /home/team01, /home/team02, /home/team03. All of us have team numbers, team01, 2, 3, and so on. But all those are linked back to the /home directory, root home team03, root home team05. All right. And under, for example, the team01 directory, there are some subdirectories there. We don't know the directory tree structure exactly, but we see some subdirectories, test, DOC, and also the C subdirectory. The C subdirectory and the test subdirectory do not contain any files, but the DOC directory does contain a group of files, all right, which we'll be using kind of like as examples as we move through this unit. Team03 has several different directories in it. One of those is PGMS, programs that contains a file by the name of suba or sub A, if you will. All right. So again, this is looking at a typical hierarchical file system structure. This is fundamental to root. Everything begins at root or /, if you will. And again, these directories have different purposes. Like, for example, the sbin directory is pretty much where the actual utilities, one of the things that is, some of the actual utilities that contain for the system to boot, for the boot process, are contained under sbin or system binaries, okay? All right. Let's clear all the drawings, including mine. Let's see what we got here. All right, path names. We mentioned that there are full path names and then there are absolute path names. Full absolute path, the same thing, but then there are relative path names. So a path name, keep in mind that everything is defined by a path. Normally that begins at root or /, okay? So normally those path names or a sequence of path names are separated by a /. So this is the path the system must follow to locate a file. For example, to locate a file PGMS, the system would go what, /home/team03 /PGMS sub A, something like that, right? And they give you the same thing here for team01 dot report. So in other words, they would go /home/team01 /DOC, and then the file under that DOC subdirectory is report. All right, so that's what they kind of specify here. Full or absolute path names always begin with a /, always begin from root. So in this case, the customer wants to VI or open the file VI/home team01 /DOC /report, okay? Or they want to specify as far as running the ls-l command out of the home team01 directory, the customer is using full path. In other words, start the path where the ls command is, which is located in /usr bin ls-l. Normally, we just run what? The ls-l against /home team01, but the customer is specifying a absolute or full path, which begins the search at where? From root or /. Absolute or full path. And then there's relative path name, okay? Start from where we are, current directory. Now we'll mention commands shortly. Let's see one of those. Let's clear all my drawings. New share. Okay. Okay, all right, came up the first time. Okay, this time. All right, so let's say, for example, okay, if I want to know my current working directory, even though I have it displayed as part of my .profile, if I type in pwd, print working directory, present working directory, shows me where the current directory from where I'm working at, okay? All right, so let me get out of this share and go back to this share. So we'll pause the share. Okay, all right. Okay. Resume the share. All right, so here, relative path name says start from the current directory. And we'll see in a few moments the current directory is always represented by a dot. Okay, we'll get to that later. Okay, so change directory to the current directory, home team01, and then VI the file name under DOC, which is report, or to CD, change directory. CD means change directory, to /usr bin. And then the dot, as we'll see later, always represents current directory. So issue the ls command -l from the current directory, which in this case is, notice the parallel here, okay? Using full versus relative path. Come here, draw. Okay. We're using USR bin, then ls-l, but the user here with the relative path is changing directory to home team01, or they're changing directory to USR bin, which is the same that they're doing here. And then dot says run the command from the current directory, which in this case is USR bin, issue the ls-l command against /home/team01. Okay. So relative path always starts from the current directory. Absolute or full path always starts from the root directory or the slash, like you see the examples here. All right. Let's clear this up. Seems to be working a little bit better this afternoon. For right now, let's see. So I just mentioned PWD. We always want to know where we are within the directory structure. Okay, you could, and you'll do this in Unit 12, Exercise 11, whereby you customize your dot profile to always show where you are within the directory structure. And I'll go back to my example because I did it, or I configured my dot profile to reveal that. So now we always show the host name and the current working directory. So if I were to change directory to /usr, then you see that what? It displays for me the /usr directory. Or if I change directory back, okay, it shows me I'm back at root if I were to type in PWD. So I modified my dot profile. I'm just going to show you. Again, you'll be doing this as part of a lab exercise later on. Okay. To show PS1, primary system prompt string, will show me my host name, and also shows me my present working directory on my command line. And that's what you see here is what? The host name, lpar1, and the present working directory is /. All right. So again, you can customize and reveal anything you want on your command line. Okay, let me go back to share. All right, where am I? PWD, some of us call it print working directory, present working directory. This command always utilizes, can be used to show you where you are. What directory are you working in? Because you always want to know that for various reasons, because you don't want to go into the wrong directory and arbitrarily remove files or create files in an arbitrary directory. You always want to know where you are. So PWD, print working directory or present working directory, always displays where you currently are within the directory structure.
Is there a difference between the PWD command and the dir command?
dir is more DOS, okay, because that doesn't work in our environment. I'll display that for you. Let's see, share. Unless you have the DOS utilities installed, okay?
Okay, that explains why it works on our system.
Okay, so yeah, see, I try to work with you, right? So if you have the DOS utilities installed, then you can use dir. But if not, like they're not installed here, then dir is not found by the shell. Yep. Okay, going back to here. It always works better in the afternoon for some reason, okay? I'm just talking to myself, okay? All right, so where am I? Listing directories, or for the most part, listing contents of directories. So the ls command will display for you with various options the contents of the current directory unless otherwise specified, okay? Basic syntax is just the ls followed by whatever directory name you would like to list the contents of. Otherwise, if you don't specify a directory name, the contents of the current directory that you are in will be listed out. Here are some of the more common, not all the options. We'll be exploring many different options with the ls command, but some of the more common options, if you will, are the -lowercase a. The -lowercase a command will show us hidden files. What's a hidden file? A hidden file are files or file names that start with a dot. For example, like .profile. Let's work with a living example. Okay, let me clear out of here. Go back to share. Okay. Currently, I'm in the root directory, right? Slash pwd, right? Okay. All right. So I perform a listing here. Okay. Notice that it lists out all the files, including those that begin with a dot, which in this case, like .profile, .spot, this and that. Because again, I've customized things for my .profile to show me, as if I'm using ls-a, all right? Normally, you don't see file names that begin with a dot. Or if I use the -a, okay, within the current directory, now, what else do we see? In addition to the spot and all that, notice what else we see. Dot and dot dot. Keep that in mind. Okay? The dot and the dot dot. When I explicitly call the -a command from the command line. Didn't get that when I listed here, but when I use the -a, I get two files. Those two files are always contained in every directory under AIX, and they serve a purpose. Okay, the dot and the dot dot, and we'll talk about that on this page, but more appropriately on the next screen. Okay, so let's go back to sharing. Okay. All right. So some of the more common options, again, we'll see other options on the next few pages, okay? But some of the more common options, keep that dots and dot dot in mind, all right? Some of the more common options are the -a, -r, uppercase, -lowercase l, -lowercase I, which we'll talk about a few of those over the next several pages. But for example, ls without any options, as I mentioned, will display the content as far as the files that are in the current directory. It will not display file names that start with a lowercase a by default. Okay? Or I should say, file names that begin with a dot by default, lowercase a dot by default, all right? But the ls-lowercase a will show file names that begin with a dot. And again, focus on that dot and dot dot. Just keep that in mind, the dot and the dot dot. Those two files. Those are two separate files, dot and dot dot. The dot profile is the name of a file that begins with a dot. Then the other files that we saw, the C, the dot, the manuals, and the test one. The same four files listed here. So ls without the -a flag only lists files that names that do not start, okay, with a dot. -a will list all file names in that current directory that begin with a dot. Dots and dot dot. Keep that in mind. Okay. ls-uppercase R. Uppercase R is a recursive listing from the current directory down to the end of that particular directory. Again, we see our ordinary file names here, or directories also. We see our file names, including subdirectory C, DOC, manuals test one. Then we see a /C. If we look back a couple of pages, DOC and C are subdirectories under Team 01, right? And C is a subdirectory also in the Team 03, but the C subdirectory contains no files. But the DOC under Team 01 does contain files. So let's see what we got here, okay? All right. So in this case, ls-r, wherever we are, we don't know in this directory structure, it will list out C, the doc, the manuals, and the test one. The C, the doc, the manuals, and the test one file. It could list out the other files, but again, the dot profile begins with a dot, right? We didn't use the lowercase a here. And then we see here dot/doc. DOC is a directory which contains three files. Okay, all right. And those three files are report, trio letter or trio letter, and also walrus. So it lists out what? Recursively, all files and subdirectories down to the end of the tree in the order as far as the directory structure. All right. So under the DOC directory, if we look back a few pages, it had the 3 files: report, trio_letter, and walrus. And that's kind of what we're seeing here with this output. Remember, the C directory contains no files. It's empty. All right. The test is empty. Now, a long list of files. We looked at the -a, -r, but -l provides a long listing. And what do we mean by long listing? A long listing of files gives us the type of file, basic file permissions, number of links, owner of the file, primary group the owner created the file under, number of bytes. So again, we see this long listing of the file. Keep in mind that the inode contains all known information as far as, shall we say, metadata about that particular file. So if we break down the fields here with this -l output, okay, the first field or the first column contains the type of file. D would be for directory, and then dash or hyphen would be for ordinary files. So we have, in this particular directory, we have 2 subdirectories and we have 2 ordinary files. By default, okay, and I'll come back to these permission bits shortly. Just break those down right now, even though we're not required, we're going to do that, okay? But come here, draw. This is the number of links to the file, okay? So we'll just say number of links to the file. Keep in mind, directory is a type of file. Okay. All right. So by default, every directory is created. There are 2 links to that particular directory, and there's a reason for that. ... And then ordinary files by default will only have 1 link to them associated. We'll come back to these permission bits shortly. Okay. The next field is the owner of the file. So in other words, the owner, who's the current owner of the file, but typically it's the person who created the file, okay, unless we change ownership or root change ownership for that particular file. The next field would be the primary group, because again, a user could have more than 1 group in their group set or be associated with more than 1 group, but this is the primary group the file was created under. Okay. So in this case, the staff group, which is the default group for ordinary users. And then the next field contains the size of the file as far as the number of characters, number of bytes of the file. So we can just simply say the size, not in megabyte or gigabyte, but pretty much we call it the character count or the number of characters, but size in 512 bytes by default. Oops. And then of course, this timestamp, and I'll just kind of highlight the timestamp out here. This field here is a timestamp field. In other words, the time that the contents of the file were last modified. Okay. Time contents of file last modified, last updated, we'll say. And then, of course, the last field contains, of course, the name of the files. So we simply say this last field is the actual name of the file or directory, keeping in mind a directory is a type of file. All right. Now let's go back to our permission bits here. And typically, they're broken down into 3 separate fields, each field having 3, shall we say, placeholders, if you will. And I'll draw a line of separation between those 3 fields, and also between the first column, which specifies the type of file. Okay. All right. So we can kind of dress this up a little bit more. So we can say the first column specifies the type of file. So type of file. All right. And then let's work with the permission bits. So these 3 fields, there are 3 fields. The first field of permissions are for the owner of the file. So that first field would be for the owner of the file. So in other words, what permissions does the owner have on the file? We'll set up permission bits formally later, but let's just understand the concept right now, okay? If we don't already. So the owner of the file, we mentioned the read, write, execute earlier. Read is equivalent, R is equivalent to a read, which is equivalent to an octal value of 4, right? We said that a write, okay, a W is a write, that's equivalent to an octal value of 2. And then there's execute, of course. Okay. Execute permission on the file, that's equivalent to an octal value of 1. Again, we don't see any numbers right now, we just see the letters, read, write, execute. So right now, if we were to convert that for the first file, that would be what, a 7, right? So don't worry about that yet. The next field is the actual group field. So in other words, the group that I want to create the file under. Okay. In this case, the group was staff, right? So any other persons belonging to the group staff or have the name staff in their group set can have read and execute permission on this particular directory, or if we go down to the bottom here, read only permission on the file test1. And then the last field, of course, is the actual others who are not the owner of the file, nor are they members of the group that particular file was created under. So that's all others who are not a group member or the owner of that particular file. All right, so that's those, pretty much this long listing generates for us this type of output. All right. And again, we'll be looking at this more so later, but this is just our introduction right now. Okay, we'll be looking at this more in Unit 5, Unit 6, more Unit 6 permission bits and such. Okay. All right, so that's the -L command. We can also combine the -L command with other options. In this case, the lowercase I. Lowercase I is for inode. So lowercase I points to, if you will, the inode number, or it will list out the inode number for the file, in this case, test1. So it gives us a long listing, permission bits and such, for the file name test1, but it also gives us the inode number for that, -L, long listing, like we saw up here, and then -I for the file name test1. So inode number 8208 is for the test1 file at this point, all right? And that's the same information we see here out of this long listing, date, timestamp, and actual file name. So that's kind of like, again, a long list of files. I know we weren't supposed to cover all what we looked at right now, but hey, just go ahead and let's do that at this time. We got to do it anyway. So now it's good, just as well time as any. All right. You'll see this again. Okay. Right. This unit is primarily about if you files and directories, not so much permission bits yet. We'll get to that in upcoming units. So let's clear out all the drawings. Okay. All right, changing current directory. Based upon permissions to a destination directory, the CD command allows you to change the current directory. In other words, the intent of the change directory command is to allow you to change directory. Now, whether you can change to that particular directory that you desire to go to is based upon permissions. Remember, okay, permissions on that particular directory. In this case, the directory being, for example, the C directory. It has permissions for the group, all others, and also for the owner. So that determines also whether you can change that particular directory. But the intent fundamentally is the CD command allows us to move, to change from one directory to another. The basic syntax, I like this now with this new update. The basic syntax is just a CD command followed by whichever directory name that you would like to change to. All right. So in this case, the customer wants to set the current working directory. So the current working directory is /home/team01. But the customer wants to move from home team01 to home team01/DOC. Give you examples here using relative path, which says what? From the current directory, absolute path always begins with what? A slash, absolute full path. So relative to where we currently are, which is home team01, we just simply type in, if we know the directory structure, of course, CD DOC. Let's look back at this. Let's make this more practical and look back a few pages at that directory structure we saw. Okay. So our current directory is /home/team01. The customer wants to go to the DOC. So if they're using relative path, currently they're in /home/team01. Simply, they just issue CD, change directory to dot or DOC. And that's what they did here, right? Change directory to DOC. Whereby our current directory is /home/team01. The customer wants to use full absolute path. That always begins at /. So /home/team01/DOC. Takes us to the same location, whether we use relative path or absolute path. But absolute path always begin with /. Now, in order to go back home, in order to go back to Kansas, tap your heels together. Nope, just type in CD, and that always takes you home. Wherever you are within the AIX directory structure, change directory or CD takes you back home. Always takes you back to your home directory. Wherever you are, no danger. CD takes you home. All right. Let's see what we got on the next page. Okay. All right. Now, they show us here the dot. Remember, every directory has at least 2 files in it. Dot and dot. All right. So now we'll identify, even though that's not our intent right now, but we'll identify what the dots and the dot always means within AIX. Okay. So let's go here. The dot always represents, and I'll put here, dot always represents the present directory. Okay. All right. Current directory, we'll say present or current directory. All right. The dot, okay, always represents the parent directory. Or another way of saying it, one directory above current. All right. One directory above current.
I have a question, Ed.
Yeah.
Well, not question. It's I'm using my Mac and I'm using Terminal, and I ended up doing the change directory to just a dot, and it kind of shows me just as me as being a user, as in the primary.
Mm-hmm.
And then if I do a change directory dot, it shows me to a everyone else. So anybody else that, like for instance, if there's anybody else on that system can access that. It just goes under user.
Okay, under USR?
No, just user.
Just user. Okay,
Yeah.
USER. Okay, all right.
User, excuse me.
Yep. Okay, that's all right. Yeah, because we kind of use those terms interchangeably. Okay, you on your Mac and you did that. Okay.
Yeah, so it was one of those things because I know the fundamentals of Mac is it's Unix based.
Right.
So that's why I was kind of wondering. I try to go into those directories, and one of them is just my directory, as in the main administrator, and the dot was just for all users.
Okay. Yeah, that, because again, all Unix doesn't work the same. It's just in his case, this is kind of like with AIX how this works. So that would be a little bit different, even in Linux, even though it's a derivative of Unix base. It doesn't work the same as far as dot and dot. Yeah. So yeah.
Okay.
That's the best that I can tell you, because that's the best that there is, when it comes to that. Yeah. So, but we can look at it some more. But yeah, it works a little bit different with different Unix-based operating systems. And HPUX, it works a little bit different. But as far as AIX, dot always sets me to the current directory. Dot always goes up one directory above the current directory that I'm in. Now, when you're dealing with, like you say, with Mac, and it's a Unix-based operating system, I don't know which one. So when you do the CD to dot, it's like, okay, it takes you to what, USER, right? To
no, it spells out users.
Yeah.
So
that's a whole different function with the dot in that particular regard. So yep. Unique instance. Okay, thanks for bringing that up. But that offers because you can see some different behavior with different operating systems regarding different commands, but also simply dot and dot dot in our case. You know, so.
Because I did the same thing in I guess our PuTTY LPAR.
Mm-hmm.
I did the change directory dot, and it just brings me just to my normal /home/
Yeah, working directory. Yep. Mm-hmm. Your
and
default working
then
directory. Mm-hmm.
if I do the dot dot, it just takes me back to /home.
Yep, to /home, one directory above, which again, you bring up good point, because that's why most admins will remove or take the /home directory out of the root BG for that very
Okay.
purpose, because it allows you, if you go up one more step, you'll be at root. Try it. Go ahead. I mean, you are okay. I mean, it's okay. You can always just set it back to CD, so you can tell the rest of your classmates what happened. Okay. And that's why admins will take /home out of the root VG, because if I'm there at home team01 DOC, if I keep CD in dot,
right.
I can CD all the way back to root.
Yeah.
Right.
And a lot of people don't like being in root.
Yeah, and also a lot of people shouldn't be in root. Yeah, so
Yeah.
we know that. Yeah, but yeah,
Okay.
that's one, because it becomes a kind of a security insecurity issue, you know,
Yes.
when you allow ordinary user to be able to be in the root directory. Yep. But yeah, good points, because again, that works a little bit differently with AIX as opposed to other operating systems. Yeah, even though they're Unix based. Yeah.
Awesome. Okay. Thank you.
Yeah. Mm-hmm. Yeah. Everybody get kind of what we were talking about. I'll show that. I'll demo that, because that's an interesting thing at this point. Let's see. Let's new share. Go up here. Okay. Because on root, it's a little bit different. Okay. Let me do this. Okay. Now let's change directory to, nope. I'm going to switch user, and I'm going to use their environment, team08. Okay. That's none of you, so don't worry about that. All right. And okay. 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 All right. Okay. So what happens is, okay, right now, if my present working directory, I'm in the directory, because when I use a dash or a hyphen, when I switch user here, okay, hyphen, so I pick up team08's environment. It's as if I'd logged in directly as team08. I pick up the environment, I pick up that path bearer, I pick up everything, because I am the user team08. So that's why team08's home directory by default is /home/team08. So what we were speaking about is, if I change directory, one directory above, so dot dot, okay, come back and look at that, I'm now in what? /home, right? If I execute that command again, CD, come on, CD, and dot dot, and then execute command, where am I at? I'm in root, which again is not a good place for an ordinary user, right? True, false, yes, no, right? So that's why admins, again, this is just something side note, will remove or take /home out of the root volume group and put it in a separate volume group, because most user created file definitions will be associated with /home by default. But by default, /home directory file system is a part of the root volume group when we install the operating system, okay? So now I'm just going to exit back to myself. So I'm just going to exit out. So I'm back to who I'm supposed to be, which in this case is what I logged in on LPAR1 as root in the root directory. Okay. And that's what we were talking about just now. Right. So go back to the new share. Okay. All right. So dot always in AX always represents current directory. Dot dot represents one directory above parent. We'll be speaking about this dot and dot dot thing again in the next unit. Okay, not so much in this unit, but in the next unit. Okay, in unit 5. Okay? Whether that begins today a little bit or maybe tomorrow, probably tomorrow more so. Okay. All right. And here's a little activity which we'll do tomorrow morning as a review. Okay. I'll make a note of that, okay, for this particular little activity here. So this will kind of bring us up to date as far as our mindset, okay, tomorrow morning as far as part of a review. So we'll continue with creating directories. Again, in or within or under AX, we can actually create directories with the make directory command. So make dir, simply we call it, creates or allow us to create a new directory. Basic syntax is make directory followed by whatever directory name that you would like to create. All right, so notice what the customer is doing here. Come here. The customer wants to create a directory, my dir, or my directory, as a subdirectory of home or /home/team01. You can use either the relative path method or full absolute path. Relative path says, okay, I change directory to /home/team01 and then create the directory, my dir, as a subdirectory under the current directory location. Or I can choose to use full absolute path simply by using make dir, then /home, which again would be full path /home/team01, my dir. Because I use the my directory command, this will create a directory by the name of my directory. Now, if that name already exists, of course, we won't be able to create that in that same file system structure in this case. All right. Keep in mind, everything is in separate file systems. Okay. Okay. So if it's within the same file system, we may not be able to use that same name within the same file system. Okay. All right. So that's one example of creating directories. Okay. So simply, we'll speak more about creating directories and manipulating directories in the next unit, but now we want to not create a directory, we want to remove a directory that's already created, all right? So remove dir command allows us to remove the specified directory. And the basic syntax is remove directory, or remove dir, I should say, followed by the directory name, all right? Now, there are some conditions that must be met in order to remove a directory. We'll talk about that after we specify our examples here, okay? So the first thing is, and the customer wants to remove the directory, in this case, home, team01, my dir. In other words, the directory you just created. Using relative path, they change directory to home, team01, and simply remove my dir with the remove directory command. Or using full absolute path, depending upon permissions, they can use remove dir, home, team01, my dir. Now, in order to remove a directory, the directory must be empty. If the directory is not empty, and you issue the remove directory command, like in this case against DOC, the return message is the directory is not empty. Okay. The directory is not empty. And you know I have a little sinister laugh for a reason, okay? Now, when is a directory considered empty? When is a directory considered empty? When it contains no file names, or is that something else? When is a directory considered empty? Think about that. Okay. When is a directory considered empty? Okay. When is a directory considered empty?
When there is no metadata available?
When there's no metadata available. Okay. Okay, that's one answer. That's good. When no metadata is available. All right. What else? Okay. What two files always exist in all directories? What two files always
The dot and the dot dot.
A dot and a dot dot. A directory, and I'll write this down, a directory is considered empty when the only items that remain in them are dot and dot dots. Okay. Okay. Let's put it here. A directory is considered empty. We'll put empty in quotes. When only dots and dot dot remain within the directory. All right. The directory is considered empty when a dot and a dot dot are the only two items that remain in or within that particular directory. Okay? So the directory is then considered to be empty. Okay? But also there's another condition that must be met. Okay? So that's one. Okay? Directory must be empty. The only items that are, can be in there are the dot, the dot, dot. There must be something else. It's pretty simple. You guys gonna smack yourself upside the head when I say it. Okay, I'll ask the
Permissions?
Go ahead. Huh? Permissions? Yeah, permissions. Okay, permissions. But even something else besides that. Let me ask you. Go ahead. Go ahead. Go ahead.
No users in it?
No users in it, right? Okay, but even something more than that. Which again, you're getting there with no users, and you said a keyword in it. Okay. Can't be in the directory you're attempting to remove, right? I was getting ready to shorthand that. You are attempting to remove. In other words, you must be one directory above the directory you're trying to remove. You can't be in the directory because you said a key thing, no users in it. You're right. No one can be in that directory, have access to that particular directory, okay, if you want to remove that particular directory. You can't be in the directory if you are attempting to remove that particular directory. Directory must be empty. You can't be in the directory that you want or attempt to remove or want to remove. Okay. Common mistake, and the reason I say it is because this happens a lot within the lab environment the first time around, because you might be trying to remove a directory but you forgot where you are. You haven't double checked that, and you're in the directory. You're standing on the carpet that you're trying to take from under your own feet. Okay. Good trick, right? All right, let's clear all my drawings here. Save that. So far, so good this afternoon. Okay. Removing directories. Okay. Okay. Creating directories. Okay. So now we look at working with multiple directories. Working with multiple directories. Okay. All right. Now you can create multiple directories simultaneously. One way to do that is with the -p command. Okay. Create missing intermediate path directories. Now, when a customer creates directories in this manner, think about this, and I'll show you, I'll just put up there a different example also. Make dir create, again, directory 2 is a subdirectory 1, and directory 3 is a subdirectory 2, which is a subdirectory 1. Or you can create it in this manner. Make dir, right? mkdir -p, and separate directories, directory 1 space directory 2 space directory 3. Okay. What's the difference between those two commands? Okay. What the example they gave us versus the example that I gave you. Okay. What's the difference? Would they
They're not
be the same?
Subdirectories in each one. They're each individual. All of them are each individual directories.
Each one of them individual directories, right? In an example that I gave, right? That
Yes.
individual directories, they can be handled individually. Whereby, if I want to remove directory 2, I've had to do what? Remove directory 3 first, right? The content in directory 3 first, because directory 3 is a subdirectory 2. Here, these are separate directories. I can work with these separately. Is there any preference, this or that? It just depends upon the environment, okay? Most of us just create separate directories under that particular directory structure, so we can work with those directories individually, as opposed to one being a sub of the other being a sub of the other. Okay. Just depends upon your requirements. Okay. All right. So you can just still create multiple directories simultaneously, or to remove all directories simultaneously. Okay. So in other words, remove dir lowercase p will remove all directories along that particular path specified. Again, this will be a little bit more difficult if directory 2 is not empty, which means I can't remove directory 3 or directory 2, or I can't remove directory 1 unless I remove directory 2, directory 3. So again, you may get errors if those directories are not altogether empty, all right? Because one is a sub of the other. So again, that's an example of working with multiple directories. Notice the customer here, they're in /home/team01. They're using this command here, make directory P, under home team01, create dir1, dir2, dir3. Each directory is a sub of the other. Directory 1 is a sub of team01, directory 2 is a sub of directory 1, directory 3 is a sub of directory 2, which is a sub of directory 1, which is a sub of directory team1, and then which is a subdirectory of home, which is a subdirectory under root, okay? Multiple directories, okay? Working with those simultaneously, okay? So far, so good as far as pass. Okay? Displaying directory information within a specified directory. We've already used, or I should say previously used, -l and -i. So now we're adding to that another option, another flag, which is -d, which allows us to display directory information. In this case, -l, d, lowercase I, provided that doc is a directory. And again, earlier we saw that it was a directory. So if not, the shell will complain that, DOC is not a directory. It will tell you. So in this case, we see the inode number. So the lowercase I gives us the inode number. Lowercase l provides a long listing. And then lowercase d, of course, provides this information for a directory. Notice that lowercase d in the first column tells us that the type of file DOC is a directory. All right. Another command that some folks find useful is under AX is istat, which is short for inode statistics. Okay, istat. It can be against an ordinary file or directory, in this case DOC. Shows us the inode number. I'll just use some parallel pointers to draw to. So it shows us the inode number. Okay, we see here 8206. Okay, shows us this a directory. Okay, gives us permission bits, as we see here, all the permission protections. Gives us the owner of the file, team01. The primary group that the file was created under, staff, okay? And then, of course, we have the link count, which again would be this. Okay? And then the actual length or the size of the file in bytes would be this. And then we have the timestamp. Notice the timestamp here. Okay? Come here, come here, come here, come here. Draw. The time that the contents of the file were last modified. But down here, we see 3 different timestamps. The time last modified corresponds out of istat to this timestamp we see. This timestamp we see here. All right. All right. But what about the last updated and last access timestamp? Okay, the last updated timestamp is the same as the last modified timestamp. But the last access timestamp is what? Is it an earlier time or later time than the last modified? The last access is what? A later timestamp, 5 minutes or so later. What do you think? And again, don't be afraid to make a mistake. Is the difference between last updated, last modified, last access?
Last access mean probably the file was accessed but never changed.
It was never changed, right? Which means I could use like a VI command, open up the file, but did not modify any content, right? But I still had to access the inode in order to perform that operation. Definitely, yes, okay, all right. Okay. Last modified, we know the contents were last modified and the inode was updated, so that reflects in that timestamp, all right? Because it's possible that all 3 timestamps could be the same. All right. So let's identify, let's work with a couple of working definitions here real quick, okay? Before we move on, let's see, everybody got this. So let's just use this page as a whiteboard, okay? Let's see what we got next, okay? Yeah, no big deal, okay? So we can finish up. Okay, yep, we'll be on time. Let's talk about, again, we spoke about working definitions for a file system, working definitions for an inode. We said an inode is an index pointer, blah, 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 this and that. But let's just give a little bit more to that right now with inodes, okay? Before I start writing, let's just give a demo on this timestamp thing, okay? And I'll use a new share, and we'll take a look at smith.log file, for example, okay? ls-l smith.log. Okay. And then I'll do an istat on smith.log. Okay. Okay. Come on, what's wrong with you? Okay. Doesn't take that long to come back with an istat on smith.log. But anyway, for whatever reason, there's something going on. But we see here that the actual last updated, last modified, then last access. Last access is February 27th, okay, 2015. Keep in mind that these systems are updated every week with makesysbees. So, all right, as far as for this particular class, okay. So last modified, last updated reflects what? June 6th, right? Current date is what? Okay, June 6th, right? Because I did go into Smith, remember, about an hour ago, and I gave you a little demo. I didn't modify anything. I just went to different screens. So in other words, a smith.log file, pretty much captures everything that you do in Smith. All screens visited, all commands ran, everything that occurs in Smith while you're in Smith, the smith.log file records, okay? Only thing I did was went in there and just displayed a couple of things, okay? But it did record that, all right? Date last modified, date last access. But notice when I use the touch command, which we'll use later on to create a zero length file against smith.log. And then reissue the istat command, istat command. Okay. Notice that now, after issuing, okay, the touch command against smith.log and then reissuing istat command, notice that all three timestamps are now the same, right? So the touch command does what? In addition to being able to create a 0 byte length file, also updates all three timestamps within the inode structure, all right? Have any of you dealt with backup programs or utilities that actually, if you read the shell script or the script, actually goes out and executes the touch command against many of those files that might back up prior to the backup of those files? They will actually touch those files. They say touch, and touch means update all the timestamp to the current date and time on those files. Okay? And that's what you kind of see here with this output, all right? Okay. Okay. Everybody okay with that explanation, that example? Okay. All right. So let's go back to sharing, okay, our screen here. Okay. Now, let's identify before we move to our last two pages before we go to lab. Okay. Okay. The definition of an inode once again. So we're saying inode, inode is a data structure that contains all known information, okay, about a file, right? That's what we said an inode was, right? An inode is a data structure that contains all known information about a file. But it's a regular file, directory, any type of file, okay, that structure contains. Okay. Now, data structure requires a different definition, right? So what is a data structure? Going back to some of your architecture questions, right? What is a data structure? That's just telling me that it's time for us to gotta go to lab. So it's a particular way, we can kind of say, particular way, particular manner. Okay, all right. So giving you the first part of this, so it's a particular way or particular manner, okay, of what?
Of storing the data.
Of storing the data. Who said that? I know you said of storing the data, right? Particular way or manner of storing the data, okay, okay, in order that what? It can be used more efficiently, right? right. All right. So I know data structure contains all known information about a file, and a data structure by definition is a particular way or manner of storing data in order that the data can be used more efficient. And that's what we're looking at as far as the actual metadata associated with the file. Okay. All right. That works, right? See, you all are doing very well. No problems at all. Excuse me. Okay. And we'll be revisiting these definitions because we'll be speaking about I-knows tomorrow again. So we'll see this and we'll see it again on Thursday. Okay, when we speak about I-knows as far as files and processes and such. All right. Okay, moving along to our last two files, which again is right on time. Okay, for us anyway, for us. So clear everything. Clear all my. See that? Won't clear. Clear all drawings. Clear all my drawings. See, it's trying to mess with me. Okay. All right. Now, file names. Nothing prevents you from using any of these characters from or within file names. These are just recommendations as far as what should and should not. Recommendations, okay? The file name, when you create a file, hopefully is pretty descriptive, fairly descriptive of the content that should be associated with that file. Okay. Recommendation, try to use only alphanumeric characters. It could be all uppercase, it could be all lowercase, it could be a combination uppercase, lowercase, okay? All right. Sometimes some customers will use underscore, @ symbol, this and that, but don't use or should not use meta characters. Meta characters like an asterisk, question mark, ampersand, and such have special meaning to the shell. When we place those within the context of a file name, the shell can give you some peculiar behavior, all right, using the parentheses within a file name. Nothing prevents you from doing this. You're root, you can do whatever you like, but you may pay the price later. Again, recommendation, the file name should not in any form, way, or fashion contain meta characters or, if you will, wildcards, okay? Again, some of these are used as wildcards also by the shell. The file name should not begin with a plus symbol and definitely not with a hash or a dash. Why? Because normally in that first column specifies the file type, whether it's a directory. This would say, well, ordinary files. So when you start including these kind of characters within the structure of a file name, the shell could, give you some unpredictable results. That file name that you're creating should not be the same name as a system command. In other words, the LSPV, don't create a file name with LSPV or who, because that's the same name as a system command, right? Shell could give you some income. And keep in mind that file names are case sensitive. Uppercase cat is different from lowercase cat. It's different from uppercase C, lowercase a, uppercase T cat. So file names are unique in that sense if they're case sensitive. And file names that begin with a dot, that start with a dot, are what we refer to as hidden files, which means that when you don't use the -a flag with ls command, those file names are not shown. In order to show file names that are hidden, that begin with a dot, we have to use the -a command with that. Then the maximum number of characters for a file is 255, version 6, version 7, version 8, AX, version 6, version 7. I can't say version 8 because it's not official yet. Version 6, version 7, AX, again, you can actually have up to 1,024 characters within a single file name. Okay, all right. If for whatever reason you need that for uniqueness, I guess. And then, of course, the touch command. We just use an example of the touch command. The touch command, as you just saw me demonstrate with the smit.log, will update all of the, shall we say, pretty much I-know instructions as far as modification, update. In other words, those 3 timestamps, update, modify, access, those 3 timestamps, in addition to access and modify, also it updates the update timestamp, okay, in the I-know. But the command can also be used to create what we call zero length files. In other words, the file will be 0 bytes in length, as we'll see an example of. So the customer here is using the example ls-l. So they're actually listing out files, all the files in their current directory, okay? All right. Issue the date command. They see the current date and time. And then issue the touch command, touch test1 and test2. Notice that they do have a test1 file, but what's going to happen with test2? So they reissue the ls-l command. We see the first 4 files that are listed here, C doc manuals test1, C doc manuals test1, but it also created what? The test2 file, which is 0 bytes in length. So in addition to your VI command to create files, among other commands to create ordinary files, you can use the touch command to create files. Just like we'll see tomorrow, you can use the cat command, C-A-T, to actually create files also that are 0 bytes in length by default. So again, various ways to create commands, various ways the touch command can be used. Okay. All right. And in addition to this little exercise here, this Q&A, we'll use these 2 things tomorrow morning for our review, checkpoint and that little question and answer, which for the most part won't take us about 5-10 minutes. We'll say 10 minutes, okay? So we'll leave that right here for right now, X file names. Okay. All right, so at this time, what we will do, class, is, okay, don't worry about Unit 5. Again, files, normally this is what happens on day 1 because, again, a lot of things going on. So exercise 2 and exercise 3, okay? Exercise 2, exercise 3, and I'll put up a little paint board, a little something there so you can actually have something to go by. But exercise 2, exercise 3, okay? 20-minute, maybe 25 minutes for the other. But again, work on it until, you know, you can either do it now, you can do it later on tonight, you can do it tomorrow morning. That's up to you. I'm just permitting time now within our context of our class to actually accomplish the lab, okay? All right. And I'll put a little board up here in a second. Exercise 2 and exercise 3. And again, this is no more lectures for today, so we are ending our class day with this exercise and also exercise 3, all right?